Hi, my name is Dai Matsuzaka, and today we're going to be working with Chapter 5.2, Congruence, Similar, and Right Triangles. So, let line A and B be parallel. So, say we have a straight line here, another line here, parallel to each other. If line C intersects both line A and B, that's line C right here. So this is C, this is A, and this is B. Now what we're saying is that these two angles, this angle is actually equal to this angle. And this larger angle over here, the obtuse one, is equal to this angle created over here. This is a important thing to just note because we're going to be using this in proving stuff about triangles later. Now I think I want to mention one more thing. Given this kind of when lines intercross each other like this, we also have that this angle right here that is opposite of this is also equal to each other. So these two are equal, and so also this angle is equal to this angle. Likewise, over here, this is equal to the angle right across from it, and likewise. So this is a very neat thing you should have in your pocket. Okay, so triangles. When we have any triangle, which is just an area enclosed by three sides, then the inner angles, which is this angle, and this angle, these angles added together will always equal 180 degrees. That's just something you should know. You should memorize that. You should be able to apply this given questions. Now, the triangles are similar if all angles are the same. So we're going to talk about similar triangles, right? Similar triangles are basically when we have triangles that are of the same proportion but different sizes. So for example, these two triangles are similar to each other in the sense that if we just scale one bigger or one smaller, we get the exact same triangle. So a good non-example would be like a triangle like this versus a triangle like this, right? These two are not similar. No amount of scaling, making it directly bigger or smaller, makes these equal. But if we have a triangle like so, another triangle like so, and these two are parallel to each other, right? Then this triangle right here, the smaller one enclosed in the larger one, these two triangles are similar. If you just increase the size of the smaller triangle larger and larger, if we take the larger triangle and make it smaller, these two triangles are going to be the same triangle. So similar triangles are literally just similar to each other. Now we're going to talk about how do you classify them. Now, one classification is that all angles are the same. So if you take these angles, this angle, and this angle, right, of the larger triangle, it equals the angles of this one, and this one right here. So if these three, all the angles are the same between the two triangles, then your triangles are similar. If one angle and two side lengths are identical, then the two triangles are similar. So if you have this side length and this side length is the same, and there is one angle that is also the same as well, then we can just connect the two sides together. And you're actually going to get the exact same triangle, actually, in this case, right? If this side and this side is equal, and one of the angles is also similar, right? It's the same, then your triangle that you can draw, right, out of these three things, the two sides and the one angle, is always going to be the same triangle. So this is good to know. And last, we have that if two angles and one side length are identical, then the triangles are similar and actually identical in this case, right? So if there's one side length and you have two angles, if you just suspend the lines out according to the angle from this side length, then this triangle created by the intersect right here, well, there's only one such triangle that will do this given these two angles. This is also the same as last time. These triangles will always be equivalent, not just similar. And equivalent triangles are obviously similar. So really, the only case in which you have to make sure that it's if it's not equivalent but similar is like this definition here when the angles are all the same. Because if the side lanes are not, right, then they are similar, but they might not be equivalent. For the other two cases, they are just equivalent. Now, if triangles are similar, their respective side lengths produce the same ratio. So suppose that we have a triangle like this. So let's call this point A, B, and C. And another triangle that is smaller but similar. We'll call this A prime, B prime, and C prime. So all we're saying is that basically the ratio of A over B, AB over A prime B prime, so the length of this over here compared to the length of the smaller similar triangle is going to be equal to the ratio comparing this large hypotenuse with the smaller hypotenuse. And likewise, this length right here, the base AC over A prime C prime, this length here is also the same. Why is that the case? Well, remember, right? Similar triangles are the same triangle, but we change the size, right, of all the lengths. But if we're changing the size of all the lengths together, then the ratio by which that is, that compares to the original triangle should be the same across all the sides, right? If we have a case in which these were not the case, right? If some of the ratios were different. So suppose that we have this triangle A, B, and C, and some ratio of, so say like A over B, A prime B prime is just 2, for example. So that means that A prime B prime must be 1/2 of this length, right? So suppose that this is roughly half. So let's call this B prime. I'm going to take A prime to be equal to the A right here. Right here. Okay. Okay. So suppose that AC over A prime C prime, so the length of the bottom, the base, is just actually 1. So AC is equal to A prime C prime. Then this point here would also be C prime. But what would happen? Well, I would just draw a hypotenuse that goes directly to that point. But it should be quite obvious that this triangle up here, the one larger one here, ABC, is not similar to A prime, B prime, and C prime. Because look, I mean, just look at the angle at the end here. I'll draw in black. The angle here, are they the same? Not at all, right? The angle here is the same because they share the same 90 degrees-ish over here, right? And over here, it looks a little bit different, but it's hard to tell. But over here, it's very distinct, right? A prime, B prime, and C prime, like this angle here, barely reaches half of what it's supposed to be. So you know right here, right off the bat, that this is not similar. So this ratio is a necessary condition for sure. Now, let us attempt a question regarding side length. Let triangle delta and triangle beta be similar. Side lengths are as follows. AB equals 1, AC equals 4 for triangle delta, and A prime B prime is equal to 2 for triangle beta. So we want to figure out what the length of AC is for triangle beta. Well, what do you know from the previous example? We know that the ratios are all equal to each other. So AB over A prime B prime is equal to AC over A prime C prime. And we want to know the length of A prime C prime, right? So just, manipulating this equation as one would do, you have A prime B prime times AC over AB. And all of these here on the right side have values, right? AB is equal to 1, AC equal to 4, A prime B prime equal to 2. Well, so then A prime C prime is literally just equal to 2 times 4, which is 8. And so you have a great way of calculating side lengths and deriving them through what you know about similar triangles and their ratios. Now we have something called the Pythagorean theorem. You might have heard this before. It's pretty famous. All it says is given a right triangle where one of the angles is 90 degrees, the two side lengths that is shorter than the hypotenuse. This one's called the hypotenuse because it's the longest one that's not adjacent to the 90-degree angle, right? So this is the hypotenuse. Hypotenuse. Now we'll label that C. So the identity is that A squared plus B squared is equal to C squared. Some people visualize this as like two squares here, A squared and B squared, and the sum being C squared. Now, you don't need to know the proof, but just memorize this identity. If given a right triangle, a squared plus b squared equals c squared. Know that you have to have AB to be adjacent to the 90-degree angle, right? C is the length of a hypotenuse. Always remember this. And that's it for right triangles. I will see you next time.